Okay, we're now ready to start talking about series circuit. Okay, so in this and all the stuff that we're going to do, we'll assume that our batteries have negligible internal resistance, and so we can just worry about the voltages that are completely supplied to the circuit itself without any loss in the battery. So let's say that we have resistors now connected in series, 3 and then so on. And we connect all these to some ideal battery that gives us a voltage of delta V. Okay. Now, just like when we were studying capacitors, okay, here we're going to have a couple of properties for the circuit. Now, when the circuit is complete, okay, what we clearly see is that some amount of current will flow through the circuit, some current I, say. And if you look at the circuit, we realize that whatever current flows through resistance R1 has to flow through R2 and R3 and so on and so forth. Like, there is absolutely no change. There is no splitting here. So the same current flows through each element in series. So what we know is that we have the same current flows through each resistor in series. Okay, and then clearly the total voltage, okay, the voltage delta V gets divided between the resistors. Okay, so in this case what we can show is that the voltage here will be, say, some delta V1, this one will have some delta V2, and so on and so forth. Okay, so we can derive using this a simple expression for the equivalent resistance for resistors connected in series. So let's see how we do that. So we know clearly that, oh, what is going on? That delta V is equal to delta V1 plus delta V2 plus dot dot dot. And according to Ohm's law, delta V is equal to I times R, where R here is the effective resistance. So we can replace that circuit up there with some circuit that looks like this. Okay. And so this gives us IR, which is equal to I times R1 plus I times R2 plus dot dot dot. And clearly all the i's factor out, so we end up getting R equals R1 plus R2 plus dot dot dot. Okay, so this is the rule for finding the effective resistance for resistors connected in series. Okay, let's apply all this to a simple example. Let us say that you're given a circuit. There's a 10 ohm in series with a 15 ohm. Okay, and we connect it to a 9 volt supply, and the question is, find the effective resistance, find current through each, and then let's say we also want to find the voltage across each. So we want to find delta V10, delta V15, and we can also go ahead and find P10 and P15. Alright, so let us see what we do. Okay, so to answer the first part, we see that the circuit is in series. So the R, the effective resistance, is going to be simply equal to R1 plus R2. In this case, we only have 2, so it will be equal to 10 plus 15, which happens to be 25 ohms. Great, good one accomplished. Now, in part B, what we realize is that now the circuit looks essentially something like this. We have a 25 ohm now connected to a 9 volt supply. Okay, so the current I is going to be equal to 9 over 25, which happens to be equal to 0.36 amperes. Okay, so this is the current through the entire circuit. Okay, but clearly because the circuit is in series, we know that this I is simply equal to I10, which is also equal to I15, and is equal to 0.36 amperes. Alright, so that's easy. So we figured that out. Now that we know the current, finding the individual voltages is very simple. Delta V10 is simply going to be equal to I10 multiplied by 10, which is the resistance. So it is 0.36 multiplied by 10, which is 3.6 volts. Delta V15 is going to be equal to I15 multiplied by 15, which is going to be equal to 0.36 times 15, which is 5.4 volts. And clearly, if you add up these two, you end up getting 9 volts. And this tells us that, you know, we're on the right path. We haven't made any silly mistakes. Also, we can find P10, and we have a bunch of different equations. To find P10, you can use any one of them. It could be either I squared R, or delta VI, or V squared over R. Okay? I'm just going to use I squared R. And I get I10 square times 10, and this gives me 0.36 square times 10, and this happens 1.296 watts. And then similarly we can find P15, which is going to be equal to 0.36 square times 15, and this ends up being equal 1.944 watts. Alright, so that's everything about series circuit.